Hi, so we are examining Laplace transform. The title of this chapter is Laplace transform. And we have done the transform from time domain to S domain. Now we will be transferring the S domain function to time domain. So this is what we have done already. Time domain functions that we faced in circuit theory are this group of functions. This is limited number of functions. There aren't so many different functions that we are facing in circuit theory for linear circuits especially. So the Laplace transform of these functions are those. So the property of these functions in S domain is rational functions. These are rational functions. These rational functions gives you some opportunity to transfer these rational functions to time domain. So the opposite of it is going to be like this. Since it is a rational function, we can write the rational functions as an expansion, partial fraction expansion. So each fraction is going to be something like that, depending on the root of the characteristic equation. So our rational function denominator is going to be characteristic equation. Denominator polynomial equal to 0 gives me characteristic equation. Denominator polynomial roots are the characteristic roots. For each root, there is going to be a fractional fraction. This, depending of this root, if the root is real, it's going to be fraction is going to be like that. If the real root is repeated, the fraction is going to be like this. If the real root multiple repeated once, it is this. If it is complex root, so the fraction is going to be two of them like together like that. Why two of them? If one of the complex number is the root of our characteristic equation, then the complex conjugate of this complex number is also a root. We know it in mathematics. It could be a repeated complex root, so it is like this, and generalize multiple repeated root case. So each of these fractions can be transferred to time domain. So you might ask, what are those k's are? K's are the coefficients that we are going to calculate when we write the rational functions fractional expansion. So we will be calculating this. Once we calculated these coefficients, these are numbers, known numbers, calculated. It could be real or complex number. So once we calculated it, then you can write for each fraction the corresponding function in time domain. So this means we are getting the inverse of our S domain function to time domain. So if it is like that positive real number, this fraction corresponding time domain function is this. Assume that k has been calculated already, so this is a known function on the time in time domain. So if it is multiple, then it is this. So you might ask us how I found that. That's easy, you see. This is what we have done repeated here. Here are 1 over k s plus a. This is this one. Time domain e to the power a minus at. E to the power minus at. Here you are. So this one is changing the columns here, isn't it? I have got these columns as fractions and transfer it to the left hand side. Just by looking at this list, I could do it. So you're going to end up with these time domain functions here. So now what we are going to do is to show you how we are going to calculate these k values. So the k values calculation depends on the type of the roots, characteristic roots that we found. So there's going to be some examples for different roots, how we're going to calculate these k values. Here is the, let me now finish this one and move the open board. Open board, open board, open board. And here are real roots. So this is the function that we found. This function could be either a voltage of an element, or it could be a Vs, or capital Vs, or it could be Is. So when you finish the analysis of a circuit given to you in S domain, you're going to end up with a rational function. This is a rational function. So you can, we are going to find this k parameters for this rational function. This is the fractional expansion. This fractional expansion, how it has been written, according to the roots in this denominator. So if you write this, this is a polynomial. This is a third order polynomial, s power s square, s, and a constant. So this polynomial equal to 0. You're going to find the roots, 3 roots. So these calculated roots are those. So that means you're going to write this with the coefficients. I am not showing it to you because the final case has been given here. So if you calculate the roots of this polynomial, you're going to end up with 0, -8, and -6. So for this root, if you write that polynomials once more, it's going to be like this. So for each root here, there's going to be a fraction. That is the fraction for this root. And for the second root, this fraction. And the third one is that fraction. Now, that is fractional expansion of this rational function. So how we are going to calculate these k values? K values has got special name. We call it residue in mathematics. How we are going to find the residue for each root? It is easy. I will be doing it for one root. So you could find the other residues for the other roots. So how we are going to do it? Let me write this rational function here, saying that 96, 8 plus 5, 8 plus 12 multiplication, s plus 8, s plus 6 is equal k1 over s plus k2 over s plus 8 plus k3 over s plus 6. So if you I will show you how we are going to calculate this k2 here. What we are going to do, multiply the left hand side with s plus 8 and multiply the right hand side with s plus 8. So each term is going to be multiplied with s plus 8, s plus 8, s plus 8. And then, oh, I made a mistake here. K3, s plus 8, s plus 6, and then replace s with minus 8. Right hand side, similar thing. So what happens on the right hand side? I multiplied each term here with s plus s, replaced s with minus s. This is going to be 0, isn't it? Multiplied s plus s, this s plus s, this s plus s, it disappears. So what is left is k2 here. For the third one, if we replace s minus 8, so that is going to be 0. If you put minus s here, minus s plus s gives you 0, so this term disappears. So right hand side is k2. Left hand side, this disappears, this disappears. When you put s equal minus 8, so it's going to be 96. Minus 8 plus 5 gives you minus 3. Minus s plus 12 gives you plus 4 over minus 8. Minus 8 plus 6 gives you minus 2. Minus 2. So this disappears. This becomes 2. So this minus minus becomes plus 96 over 4. So that gives you 4. So when you divide 96 to 4, 4, 16, 4 isn't it? 24. 24 times minus 3 gives you minus 72, which is this, isn't it? That is K2, and that's K2. So you could do the similar calculation and find out this result here. So let me write this result here. That's t-domain function. I will write it as ft is equal 120 minus 72 e to the power minus 8t plus 48 e to the power minus 6t. It says ut. Now let's interpret this result here. These are exponentially decreasing functions. We see these functions in homogeneous solution, isn't it? That is our homogeneous solution part. Homogeneous. What is this? This could be a particular solution. Since it is a constant, that's particular solution. Since this is constant, that means our independent source is DC source, isn't it? So I am interpreting that result we found here, that resulting function, as a solution of one of the elements current and voltage. So I am saying now this solution includes homogeneous part and the particular part, and from that particular part I am saying this circuit is driven by a DC source. It could be either current or independent voltage source, but these sources are going to be DC sources. Should be DC sources because of this solution. Particular solution is the solution in the form of independent source. So we can easily say these are the homogeneous solutions now. So that is an example for the real rules how we are going to calculate the residues or the K parameters here. The second step, when it is multiple roots, if it is multiple real roots, what we are going to do, it is simple, very similar to the other one, and there is one exception here. I will be calculating K3 and K4 because of this repeated root. So you could do the calculation of K1 and K2 your own, which is very similar to one that we have done already. So what is K3 case? K3 calculation, I say. Calculation. So our function is s plus 6 over s plus 3, s plus 1 square. That's why it is repeated, isn't it? Or multiple roots. K1 over s plus K2 over s3 and K3 s plus 1 square, K4 s plus 1. So in order to calculate the K3, we're going to multiply the left hand side with s plus 1 square and the right hand side s plus 1 square, 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 and then replace s with minus 1. S replace with minus 1. How I wrote it? S plus 1 equal to 0, s equal minus 1. This s replace s with minus 1. So this disappears, left hand side, we are going to replace s equal minus 1 on the left hand side. Right hand side, if we replace s with minus 1, this is going to be 0. That's going to be 0, because this is different from this one. This s1 square and this s1 square disappeared. What is left? K3 here. In here, this square and this has gone. If you put s minus 1, that's going to be 0. That disappeared as well. So the right hand side is K3. The left hand side, replace s with minus 1, gives you plus 5 here. And s minus 1, it is s minus 1 here. If I put minus 1 here, it's going to be plus 2. So it's going to be 2, isn't it? So the result is minus 5 over 2. So that's the one. K3 is equal to this one. What about K4? So we will be repeating the same thing that we have done here, but before replacing s with minus 1, we are going to do another operation. What is this operation to tell you? So it's going to be, so both sides are going to be multiplied with s plus 1 square. What is left on the left hand side is s plus 6 over s plus 3, and this disappeared, isn't it? Is equal k s plus 1 square s k2 s plus 1 square s plus 3 plus k3 s plus 1 square over s plus 1 square plus k4 s plus 1 square s plus 1. Now look at now here. So this disappears and this square goes with this one. In here, in the previous one, in the calculation of K3, I replaced, after multiplied s plus 1 square both sides, I replace s with minus 1. In here, I will be a process before replacing s with minus 1. what is this process? Is getting the derivative of this, both sides, with respect to s, d over ds. And similarly, right hand side is equal d over ds, and then replace s with minus 1. So what happens is this now, right hand side first. So when you take the derivative of this one, it's going to, and then replace s minus 1, this term is going to disappear. Why is that? Because this is a ratio, isn't it? So we're going to find the derivative of this one, multiplied with this, and then minus derivative of this, multiplied this. So it's going to be in parentheses of s plus 1 parentheses. I can put that resulting derivative. I will do it for this one, for example. So derivative of this with respect to s. So k2, leave it as it is. And derivative of the numerator is 2s plus 1 multiplied with the denominator, s plus 3. Minus denominator derivative is 1 multiplied the numerator. Numerator is s plus 1 square over s plus 3 square, isn't it? What I have done is get the derivative of this because of that. So that is the derivative of it. So, and then you're going to, so if you look at that derivation now, the derivative, this s plus 1 here is common in both of this. So I can put the whole formula here in parentheses of s plus 1. If you replace s with minus 1, that's going to be 0, isn't it? Because of that coefficient. So that's going to be 0. Similarly, square of s plus 1 on the numerator is going to end up with a derivative in parentheses of s plus 1. So that's going to disappear as well. So this one is going to be is a constant here. These are already disappeared. The derivative of a constant with respect to s is going to be 0. That has gone as well. What about the derivative of this one? Now that square has gone and this one gets. So what is left is this. Derivative of this function now, which is this, is k4, isn't it? Because derivative of this function with respect to s is 1 times k4. So what is left on the right hand side is k4 only. So I am going to get the derivative of this function and replace s with minus 1 in order to find that k4 here. So let's do it now. Derivative of this numerator is 1 multiplied with the denominator as s plus 3. Derivative of this, which is s square plus 3s, derivative of the denominator minus 2s plus 3 multiplied with the numerator s plus 6 over s square plus 3s, and I will be replacing this s with minus 1. What you get, so this minus 1, and that's going to be minus 1, that's going to be 2, and this minus 1, this is minus 3, so that's going to give me 1, minus 1, that's going to give me 5, isn't it? So this is minus 2 minus 5, numerator is going to be 7, minus 7, sorry, minus 2, okay, minus 2 minus 5 is minus 7. So minus 1, this is going to give me square of it is 1, isn't it? So that's going to be minus 3. So that's going to be minus 2 here. So minus 2 here. So it's going to be 7 over 2 is equal to K4. So I just show you how you calculate K3, that K3 here, and K4 here. So you could do K1 and K2 calculations your own. What you're going to, once you have done the calculations here, calculate K1, K2, K3, K4, rest of it, in order to transfer this S domain function to time domain function, we're going to use the list. In this list, for this one, we are going to replace it with this, isn't it? So A here is 3. So it's going to be e to the power minus 3. Here are minus A, it says. For the multiple case, which is this case, the corresponding time domain function is going to t times e to the power minus A. A is 1 here, isn't it? So that is A. So it's going to be t minus t. So for this one, this. For this one, this. So these are given to you in the exam or anytime you like. You can look at these lists. Laplace transform list it is called. So in the list these are available. By looking at those you can write the function in time domain as it is like that here. So we have done this. Next step is the multiple root, this time third order multiple root. So this one you could do it your own. I didn't give this one, but we examined this one now. I gave it to you. So you could do your own, find out all these K1, K2, K3 and transfer it to time domain, find out this. If you couldn't do it, that means you didn't understand that. So the last one is going to be the complex conjugate roots. Exist in the fractions, then how we are going to find out the residues for these fractions. So here you are. If you look at this rational function here, the characteristic roots are this complex conjugate root we've got, and there is a real root as well. So altogether there are 3 roots, characteristic roots. Therefore there are 3 fractions here. One of them for the real root, the other 2 for the complex root. If there is a complex root, we know complex root as a, if you have a complex root, then complex conjugate of this root is, complex conjugate of that number is also a root. So the one thing that I've got to explain to you in mathematics, it is possible to prove that this is a complex number and that is the residue for this complex number. So this residue is also going to be in general a complex number. On the other hand, for the next fraction here, you do not to calculate this K3 complex number for this complex conjugate root, because it is mathematically can be proved that K2 is complex conjugate of K3. So if you find to K2, then you can find the K3 as well, as it is shown here. Mathematically it is possible to prove that. I'm not going to prove it here. But I would like to give you a calculation of K2. I'm not going to do it for the K3 because I know K3 is going to be complex conjugate of K2. So let's do it then. How are we going to do it? So left hand side, very similar to real roots, there's no difference for that. So 100, 8 plus 3 over 8 plus 6, 8 plus 3 minus 4j, 8 plus 3 plus 4j is equal k1 s plus 6 plus k2 s plus 3 minus 4j and plus k3 s plus 3 plus 4j. So we are going to multiply both sides with this one in order to calculate that k2. So s plus 3 minus 4j, s plus 3 minus 4j, s plus 3 minus 4j, s plus 3 minus 4j. And then replace s with minus 3 plus 4j. How I found that? So if you write s plus 3 minus 4j equal to 0, s is minus 3 plus 4j. So after that multiplication, this disappears and this disappears. On the right hand side, this disappears, this disappears. And if I replace s with minus 3 plus 4j, then this becomes 0. You see, if you replace s here, with this, minus 2, 3 plus 3 gone, isn't it? That's the opposite. That's going to be 0, isn't it? Minus 3 plus 3 gone, minus 4j plus 4j gone. Similarly, this is also gone. This already gone. So what we have on the right hand side is k2 only, isn't it? Is equal to what? Now I'm going to replace 100. S is minus 3 plus 4j. I wrote it for this s now. That is that s. And that is that s. Plus 3 over minus 3 plus 4j, that is this s, plus 6. And what is left, this has gone, so we've got this. So plus s, replace minus 3 plus 4j. This is for this s. Plus 3 plus 4j. So if we do this operation, it's going to be this gone, k2 is equal 400j over, so this is plus 6, isn't it? That is plus 6. So minus 3, so 3 plus 4j, this gone, plus 8j. So that k2 is equal to this one. If you do this calculation, you're going to end up with this. And then we found k2. So in polar coordinate is equal to this one. So for K3 in polar coordinate, complex conjugate of this one. So we found the K2 and K3 in one go. You don't have to do K3 calculation once more, because I know K2 is the complex conjugate of K3 is equal to complex conjugate of K2. So once we have found this K, then we can transfer this two term to a time domain function as written here. How I have done it, this is available in our list. So I'm going to replace this one with the time domain function. So this K here is this K module here. So this is K module, that is. And this minus 53 degree is the angle of K. So this is now 10. The theta here is minus 53. These two things are related with the residue that we found here is related that K2. So what is left here, this is e to the power minus alpha t. This alpha here, make it different color. And this beta here, what it is. This alpha is the characteristic root real part, which is minus 3, which is this. That is characteristic root is minus 3 plus 4j. So this minus 3 here is the alpha here. That beta is this beta. So beta is 4, is this 4. Let me show it to you. That is that 4. That is that 3. So these green ones here are related to the complex root, and these red ones are related with the residue, the K parameters here. So as we have found the K's and we already know the characteristic root, then we can write this here. If you do this writing, you're going to end up with this. Now let's interpret that result now. What solution is this if this rational function is related with one of the elements current and voltage? So if you look at this one now, all these terms has got exponential functions here. Since these are the exponential functions, so I can say that this could be a homogeneous solution. Homogeneous solution. So there is no particular solution then. Let me clear that. That's not good. Make it a bit better now. So I'm talking about this solution here is homogeneous solution, I'm saying. So there is no particular solution. So what you can say about that solution is a natural solution. Why is that? Because no particular solution means there is no independent source in the circuit, isn't it? Because particular solution is the solution in the form of independent source function. Since there is no independent source function, there is no particular solution. So how we can get without any independent source is left is what is left in order to have a solution like that is the energy source coming from the initial conditions. Initial conditions exist, but no independent source. That is the definition of natural solution, isn't it? So that solution is homogeneous solution. At the same time, it is a natural solution. That is end of this video.